Okay, so the next speaker is Sotiropoulou. She has received a PhD from the Aristotle University of Thessaloniki in 2014, and she has since then grown her experience onto a very wide background, ranging from compression, image and video processing, high performance and real-time systems, radar and biomedical application, and also she worked on the upgrade of the Atlas detector here at CERN. So now she's an electronics engineer and sales engineering manager at CAST Incorporated, and she will present today high-speed UDP TCP hardware stack IP, focused on high throughput and low latency. Thank you.
Now, can you hear me? Perfect. Okay. Thank you very much for this opportunity. It's good to be back here after 7 years since my last TDAC integration. We are going to discuss hardware stacks of 100G and over. First of all, I have to say that it was a rather interesting choice by the organizers to put an IP vendor after something completely free, like OpenLogic. But for those who don't know who we are, CAST is one of the first 3 IP vendors in the market of electronics. We were founded in 1993. The company is an American company. The headquarters are in New Jersey, but we are truly global. We have engineering groups in both the US and Europe. We have sales engineers in both US and Europe. I'm based in Italy. And we have representatives that sell course for us in Southeast Asia and India and all over the world. We have a very extended portfolio in communications, hardware stacks, course for data centers, automotive, video, image codecs, data compression, and peripherals. So here we are going to discuss today hardware stacks, UDP and TCP. UDP and TCP are the 2 protocols that are mostly used for Ethernet connections. Okay. UDP, the user datagram protocol, is a connectionless protocol. It doesn't have requirements for opening, maintaining, and closing a connection. It's always best effort, so it's not secure. There's no handshaking, so you cannot be sure that the receiver has actually received the packet. But it's more lightweight, it's simpler to implement, it has smaller overhead as a packet header, and it's mostly used for streaming applications such as video, audio streaming, etc. While on the other hand, the TCP, the transfer control protocol, is connection oriented. There you have to open a connection, have to establish a connection and have a handshake. So there is a flow control, and it's more complex. This is why it's better used in applications that require control. So why use hardware stacks? Why? So if you don't use a hardware stack, what has been going on for years is that hardware stacks, UDP and TCP, has been implemented on software. So to start with, on FPGAs, in order to use it on software, you have to have a processor, a microprocessor. So either have an embedded processor. So by definition, you need a more expensive FPGA that has an embedded processor, or you need a larger FPGA that you implement the soft processor on it. Okay. Then the soft processor will use several giga instructions per second in order to implement the UDP or TCP stacks. You have several million of accesses on the buses, on the memories, so power consumption. Okay. And you have arbitration, increased latency, loss of consumption. While on the hardware stack, if we use a hardware stack, you basically, for UDP, you don't even need a processor. Okay? You just program it with the control and status registers. It's a lower design complexity because there is a straight pipeline from the user application to the hardware stack, to the MAC, to the exit. And you have a lower power, obviously, because you don't need all these surrounding elements like external memories, buses, processors, etc. Let's go to the discussion about why over 100G and over hardware stacks. I feel lucky because there was the presentation by Sophie in the first part, because there was this continuous discussion about 10G transceivers and 100G transceivers and how these new FPGAs, you're going to have 400Gs for the scientific experiments, etc. And this is true. This is not just for scientific experiments. We see it in our customers in industrial applications, in data center applications. We've had customers that come with requirements for data transfers 100G and over on FPGA devices, for applications like high-performance computing, data centers, and others. So these applications have now real-time requirements that push it beyond traditional software. Handling this kind of networking demands on software is no longer feasible because it just cannot keep up with the requirements. So you need a hardware stack. Why do you need a hardware stack? Because it's deterministic, it's scalable and it's efficient, and it offers predictable connection, predictable latencies, and it's always scalable, and this is very important and for applications such as streaming and control. Okay. So how do you measure the performance of a hardware stack? The first thing you need to know is the latency. The latency is the time it takes for the data to travel through the hardware stack. The lower the latency, the faster the response time, and the better real-time behavior you have in your hardware stack. The second metric is the throughput. The throughput is the amount of data that a stack can process per unit time, per second, the gigabits per second that we discussed. A higher throughput means that you have better utilization of the link capacity, which is specifically important in links of 100G and over, okay? Because there you have discussed overheads, etc. So what happens here? The traditional software, as we discussed before, it struggles with the requirements of 100G and over that. Why? Because you have an operational system overhead, you have the memory copies, you have unpredictable latencies, you have lots of things competing over the same resource space. Okay. The latency of software, when you have a software stack, it can be as high as 50 microseconds and much higher than that in other cases, which in real-time applications is a nightmare. It's not feasible anymore. Well, when you have a hardware stack with UDP or TCP, you have a predictable latency and you have line rate networking. A hardware stack needs to be 100% RTL code. In the cast hardware stacks, we don't use embedded CPUs. We don't use microcontrollers. They're vendor independent. They can even be used on ASICs, and there is no microcoding inside it. The cores themselves have very deep pipelining. They have internal parallelism, and this increases the throughput by increasing the bus sizes and the clock speed. Okay, so you have the basic fundamental design that is the same from 1G to 100G, but then you have to increase the parallelism, optimize the throughput, etc. And you also use the hardware stack for protocol acceleration, such as what needs to be done for the protocol itself, the segmentation, calculate the checksum, and reassembly the packages. Let's discuss now the basic characteristics of the 100G UDP-IP core. First of all, it can execute full protocol offloading. Once you use a hardware stack for UDP-IP, you don't need a processor. That's it. You can forget it. If you don't want it, you don't need to implement it. It implements transport, internet, and link layers. It can have up to 32 TX transmission channels and up to 32 receive channels, which is a little bit relative. It actually can have more, but depends on your resources and the complexity of the design you want. It has a 512-bit bus, and it needs a clock of over 250 megahertz. Now, here comes the question. If you make a calculation, you say 512 bits on the bus per one clock cycle of 200 megahertz, it gives you already 100 gigabits per second. Why do you need over than that? You need over because you have several overheads, be it the bus overhead, the protocol overheads by the several wrappers. You have like the UDP protocol wrapper, the IP wrapper, etc. So you need to take into account all of these things. The core itself has two separate clock domains for data and control. It can also use jumbo frames up to 64 kilobytes. The basic configuration you need to know for your UDP-IP core is the number of RX and TX channels and the size of the buffers that you want to use. So let's give a basic example. A basic configuration with one transmission, one receiving channel, and a buffer of 32 kilobytes, okay, per channel, has a size of around 10,000 LUTs, and uses around 28 VRAMs. We are talking, the example is from an AMD UltraScale device, plus device. Okay. If you take the same configuration with 16 channels in the transmission and 16 channels in the receiving side, and again the same size of buffers, the core becomes 27,000 LUTs and 133 VRAMs. What is important to notice here is that the core doesn't grow linearly when you increase the number of the channels, okay? So we have optimized the design of the core in such a way that by increasing the number of channels, you don't increase linearly the size. Let's go now to the more complex core, which is the TCP/IP core. It has, again, full protocol offloading. It can handle up to 32,000 sessions. It has simultaneous client and server support. It implements port and IP address filtering for incoming connection requests, and it optionally supports UDP. Basically, the custom TCP/IP core is an extension of the existing UDP/IP core, so with one core you can have both. In this case, the configuration you need to know most importantly is what is the maximum number of sessions you want, and the maximum number of servers and ports. So let's take, again, a basic example. Suppose that we have 16 sessions and 8 servers. This core has a size smaller than 50,000 LUTs. It would be like 46, 47, and around 20 VRAMs. If you go to the same configuration with 16,000 sessions and 8,000 servers, it has a size of exactly 50,000 LUTs. It will be 49 something. So you see that the logic itself has changed it was a very small, insignificant change in the logic. What changed a lot, though, is the VRAMs, because now you need 980, and it's obvious because you need the buffers in order to buffer all these sessions. So to add to that, you need to take into consideration you also have partly a UDP core together with it. So you have to add the resource of the UDP configuration that you want to add to your TCP configuration. That's the total size of the core. Now let's take an integration design example on an FPGA. Let's say an AMD UltraScale Plus. So let's take it from the exit to the inside. First, you have the transceivers, a GTY transceiver. The transceivers have an interface with the fabric, the FPGA fabric, which is a KOE 4 or 10 for the UltraScale Plus. These are 4 interfaces of 25 gigabits per second each. This is how it works on the specific device family. The interfaces connect to the MAC PCS IP from AMD. This is provided by the vendor, which is a subsystem. And then you go to the inside, and this gets connected to the UDP/IP core, the 100G. These 2 cores are connected with the AXI stream interfaces. That's 512 bits. Then you have your user application, which is also connected with a 512-bit AXI stream interface. Now, it is a streaming interface. If it's another vendor, it will be an Avalon stream interface. So just basic principle of it. Then you have the memory mapped bus. And you have the controller status registers from both the UDP/IP and the MAC PCS IP that they just need access to be programmed or read by the memory mapped interface. You just need optionally to have a microprocessor or an FSM to program these registers. You don't need it. Now, that part, the part that is in this rectangle of designed here, CAST provides is already pre-integrated, so you don't need to worry about integrating the UDP/IP core with the MAC from your design, from your vendor, whatever vendor this is. You just get it already prepared, and you just need to worry about what you do with your user application. And as I said, the the optional part is the microprocessor, that you don't need it, actually. Another option, though, is that if you have a user application that doesn't have a streaming interface, so it's not a continuous pipeline of data that come from the user application to the hardware stack, and they go through a memory mapped bus to memory, external memory, you can also do that by using another core, like a scatter-gather DMA, okay, that will give you a master access to the memory bus, to the memory mapped bus, or a MM2ST, a bridge from memory mapped interface to AXI streaming interface that will give you a slave access to the memory mapped bus. But again, this is always feasible, and it will still give you the 100G you need. Now, let's discuss a very important aspect of this course and the networking requirements, the latency. There are three types of latency that we need to take into account. First of all is the MAC layer latency, which is the latency of the Ethernet MAC IP. It takes the time it needs to process the data as they come in and come out of the MAC. This is completely vendor dependent, so it has nothing to do with the hardware stack. So if you want to calculate your MAC latency, you just need to read your vendor's user guide because it has nothing to do with the external hardware stack. Then we have the UDP and IP latency, which is the latency of the core that the core introduces while processing the received packets or generating the transmission packets. And then is the ARP latency, which is a latency that comes in place when you want to transmit a packet, but you don't have already stored the physical address inside the hardware stack. So you need to resolve this. You need to ask the network who has this IP, who's the physical address. So there is interaction there. So this is the only one that's not deterministic in a hardware stack because it depends on the traffic on the network. So let's discuss the UDPIP on 100G latency on the receiving side. This latency is measured from the boundary of the MAC to the boundary of the user application. Okay, because the UDPIP core needs to store all the information from as it receives the packet in order to check the checksums before sending it to the user application. Okay. So how would you define the latency on the receiving side is the time between the end of packet, when you receive the end of packet from the MAC to when you receive the start of packet in the user application. Okay. And this needs to be measured without taking into account possible bottlenecks by the user application, because otherwise this is not the pure UDPIP core latency. This is why to measure it, we use the ready signal. In the cast UDPIP core, this latency is only 17 clock cycles. And for a system clock that's 322.26 megahertz, which is the clock that uses the MAC PCS of AMD for ultra-scale plus devices, this is only 52.7 nanoseconds. So think about the latency we discussed about software at the beginning of this presentation, that it's the smallest we can calculate is around 50 microseconds. You can see like we are 100 times less and even more, and like many orders of magnitude less latency when you use a hardware stack. This is very significant. And this is how we calculate it for the simulation from here to here. These are 17 clock cycles. The TX latency on the other side, the transmission latency, it is affected by the ARP protocol. So we said, if you know the physical address, you don't need to resolve it. But if you don't know the physical address of a specific IP, then you need to ask the network who has this IP address and resolve it and get them the physical address. It depends on the UDP payload size, because the buffer needs to store the complete packet in order to calculate the checksums before sending the packet on the network. So a bigger packet, obviously bigger latency. And it also depends on channel arbitration. Why? Because when you have more than one channel, there is a round-robin priority, an arbiter. So you need to wait for the one channel to finish the transmission before you go to the next, the next, the next. So this adds latency if you have many busy channels working in parallel. So let's start with this example. We suppose we don't have the physical address. We don't know. We have the address in the ARP cache. So we send a message. The message is, sending the message lasts like 19 clock cycles. Then the response comes from the network, because in this case it's just a simulation. The best case scenario is in the simulation just takes 2 cycles, which is not realistic. Okay? But as we said, this is the only thing that doesn't depend on the core itself. It depends on the honor code. It's not deterministic in this case. Okay? Then you have received the ERP packet and you process it in order to resolve the address. And this takes 44 cycles. And then you transmit the packet, which will take 22 cycles. Again, if you take into account a 322 megahertz clock, these are a few nanoseconds again. Again, the order of magnitude is several times smaller as a latency. So, what CAST has to offer about hardware stacks? First of all, CAST has a very long experience in developing hardware stacks. They are developed, all of them are developed in Europe by our groups in Europe. We have one group that's based in Brno that does the development of the UDPIP cores. And we have a group in Greece that does the development of the TCPIP cores. We have a 1G core, 10G, 25G core, 40G, 50G core, and 100G UDPIP core that have been productized tens of times on both FPGAs and on ASICs as well. And we currently offer a TCPIP 1G, 10G core, okay? And we will release very soon, in a few months, the TCPIP 100G core, and soon after that, the 25, 40, and 50G core. Okay? And we have in progress an IPv6 core that will come probably this year. So there is a very full portfolio by CAST. So let's conclude. Let's discuss this again. So 100G networking. It requires hardware solutions. Why? Because software, as we said, cannot keep up anymore with this kind of requirements. The latency is too big for real-time applications. The hardware stacks are the solution. Why? Because they deliver deterministic performance. A fully hardware-based UDP TCP/IP core has low latency, high throughput communication, and it's ideal for scientific, industrial, and data center applications. The hardware stacks have efficient resource utilization. They're scalable, they are very efficient, and also their size doesn't increase linearly with the complexity of the core. The CAST hardware stacks, as we know, because of our long experience in this sector, they are ready for real-world deployment. They're foolproof and full productized, and they can offer you easy, seamless integration into FPGAs for both UDP and TCP/IP solutions. So if you have any specific questions, you can ask now, or you can contact us at CAST in the emails here. And I have to say one thing, okay, best things in life are free, but best hardware stacks aren't, so yeah.
Thanks, Calliope. Let's thank. And we open the floor to questions. We have one to the left.
Is it a Xilinx AMD only core, or does it also support other FPGAs?
Where are you? Okay, closer to the microphone, please.
Sorry. Is it a Xilinx only core, or does it support other FPGAs too?
It is vendor independent. So
okay, so you're not using high-level synthesis?
Sorry?
You're not using high-level synthesis?
No.
No.
Forbidden word.
Good idea.
No. It's Verilog. It's 100% RTL. It's Verilog. Yes, Verilog cores.
Okay, thank you.
We have a question.
Thanks for the presentation. So I think you mentioned you have different clocks for controller and data path, right?
Yes.
Why did you need to do so?
They're not. You need to have like think of the clock rates. If you have the AXI for the memory mapped link, the AXI for light of the system has a specific clock rate. That doesn't need to be 322.26 megahertz. So you have a much lower clock for your AXI memory mapped interface, and you have a faster clock for the data path. So yeah, you need to keep it independent to facilitate the user integration, basically.
Thanks.
We have another question there.
As was mentioned before the coffee break, for, say, FCC at CERN, we're going to probably want to go above 100G. Are there plans to develop IP cores for this as well?
Yes. Though the plan is to go to 400G, clearly. But just small parenthesis here. This core, as it is now, the 100G core, we have sold it for ASICs, and they use it as a 400G core because you can simply overclock it. The limit is the clock frequency on the FPGA device right now. Okay. Basically, there is a certain degree of flexibility by by our customer requirements. Okay. Even in definition, you can use the 1G core, which has a 32-bit bus, as a 10G if you overclock it. Or you can use the 10G, which has a 64-bit bus, as an 1G if you have a lower clock. It depends on what the user wants to do in the integration and what the size of the data path, which MAC they will use on the other side. So the limit here is the degree of parallelism on the bus and your clock frequency. So the same core on an ASIC that has no limit, that doesn't have the constraints, the clock constraints of an FPGA, it is already a 400G core. We are working on it to produce a 400G UDPIP core. It is in the pipeline now. The first thing that we want to release is the TCPIP 100G core that will come very soon. But the obstacle here is what comes from the vendors. So when we say our UDP cores, that whatever we have for 100G, I keep discussing AMD and Altera. Why? Because the others don't have it. So I cannot say I can productize it on a Lattice or any Phoenix since they don't have an FPGA that offers the transceivers in order to do it, right? So it has to do with the technology as well.
We have a question from Francesco.
Hello. So I developed Hog with David, this system to maintain code on Git. Mm-hmm. So if someone uses something like that, what does it look like? What is it that are you allowed to put it on version control on Git? So do you have text files that can't be shared, or is it a precompiled library? How does that work?
Look, now you go to licensing terms, okay? But the core, we sell RTL code as well. So if when you buy very low code, it is very low code. You put it on GitHub, you can do whatever you want, but within the limits of your license agreement. It's not OpenLogic, it is a cast IP core, but yes, it is pure Verilog. It depends on what the customer needs. And does the customer need a netlist? Does the customer need encrypted RTL? But we also provide fully visible RTL code. Think that we have customers that do functional safety systems. So they need full visibility of the source code because they need certifications. So we offer full core visibility when the customer requires it.
Okay, thank you.
But I guess in that case, I mean, if we have an open source project, we cannot put your license, you mean your core on our repository, for example?
No, it cannot be. It can be used for academic purposes, but cannot be posted freely. Yeah. We have academic and research customers. Okay? We work closely with academic institutes and research institutes that use our course. Actually, we have been contacted by Atlas institutes as well. But it cannot be shared freely after that. It needs to be used within the limits of the core, of the project, yes.
Okay, I would invite any other questions to be addressed to Calliope at the CAST stand just outside, so we can thank Calliope again for this interesting.
Thank you.